Welcome to the last section for this Math 1127 course. We're going to look at contingency tables today, and again, it's pretty much how to do some calculations with the technology of your calculator. So make sure you have that handy. First of all, what is a contingency table? It's kind of like a two-way frequency table. We have frequency counts of categorical data that goes to two different variables. So that sounds confusing, but it's going to make sense when you see it. A contingency table will have something listed in rows and then something else listed in columns, such as maybe males versus females, who said yes and who said no, so that it's kind of got two things going on at once there. When we deal with the contingency table, we need to do a test of independence. You're going to test the null hypothesis that the row and the columns are entirely independent. There is nothing that is going to make one of the variables in the columns change just because you change the rows. So always, 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 these are the null and alternative hypotheses for this. The null is that the row and column variables are independent. Independent, okay? They are not connected. And then the alternate hypothesis is that they are dependent. So how do we go about doing this test, and what do we have to have required? So again, you have to have randomly selected data. That's pretty much a standard throughout this course as we've done. If you have some that you don't know are randomly selected, we're not saying you can't do this test, but the results might not be valid. You have to have a two-way table. It doesn't have to be a 2x2, don't confuse me, but you have to have some stuff in rows and some stuff in columns. Every cell in the contingency table, like maybe by cell we mean maybe the third row, second column versus the third row, first column or something. So for every cell, the expected frequency, expected starts with an E, and we denote the expected frequency by an E. You have to have an expected frequency of at least 5. Now there's a formula for how to calculate the expected frequency, but really we can get your calculator to do that for you. Not every single one of them in the observed, so again, observed frequencies, we know with O. You don't actually have to have an observed value of 5. You have to have an expected frequency of at least 5. We do a chi-squared, so this is pronounced kind of like K-I with a long I, not the CH sound that you might would think, but it's chi-squared test. And a chi-squared is it's actually another Greek letter that kind of looks like a capital scripted, and I'm not going to be able to do one, but it's going to be a scripted capital X. So a chi-squared test is what you want to use for a contingency table. And here is an example of one. This one comes from looking at when people have some sort of stress fracture, if they have surgery versus just a cast or a non-weight bearing cast, and that can be separated into less than 6 weeks or at least 6 weeks. The outcomes of that surgery or treatment, the outcomes of the treatment could be considered success or failure. Did it take care of this problem? And so we have counts. Now there's a lot of people that had surgery, so we have more numbers up here, as opposed to people that actually have non-weight bearing cast for fewer than 6 weeks. So that's a smaller number there. But we can take even these, they don't have to have the same number of trials in each one. We can take something like this and we can test a claim that the success of treatment is independent from the type of treatment. Okay, so that would mean that whether or not you're successful or a failure on the treatment outcome has nothing to do with the type of treatment you get. Now on the next screen we've got some calculator instructions, so just stay with me and we're going to tell you how to do this on a calculator. So we're going to test this and then we're going to say what the result indicates about the trend to use surgery. And you notice, as I said before, there were a lot more surgeries than just this last category. However, there's still a lot that just go into this weight-bearing cast. But what we're really going to test here is, does the type of treatment affect the outcome of the treatment? Do they go together? All right, so there's quite a few things to click. By now you're a little bit used to that, but to enter a contingency table, you have to enter a matrix, and we've not done that in this course before. To get to a matrix, you're going to hit second, and then your x to the -1 key, and just above that x to the -1 key, it says matrix. So we'll enter that, and then we hit edit. So again, to show you where that is on the calculator, from your regular run screen, we go second, and the x to the -1 key is this fourth key down in this first column, not counting that top row, I guess. So I just pressed that. I didn't even have to hit enter, but then I need to hit this right arrow key to go over to edit. All right, now I have two matrices here, but you only need to enter the one. What's going to happen is, even if you don't have any dimensions there, like all these other ones don't have dimensions, if you don't have any dimensions, don't worry about that for your second one. Don't even worry about it for your first one right now. We're going to enter those so that you can have it. And the reason I actually have them is because I've already entered this to make this PowerPoint. But right now I'm going to hit enter because I'm actually wanting to edit matrix A. If I wanted to edit matrix D, I would go down and then hit enter. Okay, so I'm going to hit enter. And in fact, even though I have this in matrix A, I'm going to show you how to do it for matrix C maybe, so that you can see what it would typically look like. So if I said I wanted to go over to edit and I wanted to go down to matrix, now I want you to put yours in A. It's just the easiest thing to do. But notice here, when I went to a place that didn't already have a matrix, it says 1 by 1. So that's where you need to notice it needs to be rows by columns. So you will need to count how many rows of numbers you have and how many columns. So in our previous slide, we had 1, 2, 3, 4 rows, and I had just the 2 columns. So that is a 4 by 2, because when you're doing this, it's already rows by columns. So when you are entering it, even though you're entering on matrix A, that's where you're going to put 4 and then 2. Suddenly you have enough spots to put all of your numbers. Then you're just going to type each of the numbers from your contingency table into that. And always just remember, this is rows by columns, so you can change those dimensions if you end up with a larger or smaller contingency table. Now, after you get them entered, which I already had them entered in matrix A, then you're going to go to, I think we've done this other part before, you're going to go to stats and test, but we are using a new test this time. You want the chi-squared test. So the chi-squared test, you're going to have to scroll down, you know, it's way down below this. We had that Lin-Reg test, but chi-squared test is option C, so you will have to hit stat, test, and then hit your down arrow key until you get to chi-squared. All right, when you do that and you press enter, the next thing you get is a screen like this. Now, observed needs to be wherever you put it, but it does automatically come up as matrix A. And so that's why I wanted you to put it in matrix A. Now, if you needed to change where it was, that is possible, or if somehow yours doesn't say matrix A, if I go to stat, test, and then I'm going to scroll down until I get to that chi-squared test. If you did not have an A here, so see, now I don't have it, or you have the wrong thing here, the way to get that matrix there is just above this -1. It does say matrix, so I'm going to hit second, x to the -1, which is my matrix menu, and then here I'm not editing it, I'm just picking the right one, so I'm just going to hit enter. And notice it put that matrix A back. So I believe it'll have your A and B. If it doesn't, go ahead and put it. And I know we have not entered a matrix B. What's going to happen is it's going to take all of your observed values that you have entered from matrix A, and it's going to calculate expected values for you and put them in matrix B for you. So this is kind of where it's going to put all of those expected values. An interesting thing is it may calculate it, but you're not going to see them next, even though your homework could ask you for an expected value before it asks you for the other thing. So you might just kind of need to go through this twice. So then I'm going to hit calculate, and I get a chi-squared value and a p-value and a degrees of freedom. Okay, so that chi-squared value it gives you is your test statistic, not your critical value, but your test statistic. P equals is your p-value. Now, degrees of freedom is calculated differently for this. So you have rows -1 times columns -1, just to let you know where that comes from. So since I had 4 rows, I had 4 minus 1, which is 3, and then 2 columns, but 2 minus 1 is 1, so I ended up with 3 times 1, which is 3. But that's how that degrees of freedom is calculated. But your calculator will find that for you, so you don't even have to find that, okay? These are the 2 values we're going to use in looking at our test and evaluating our test. So this is that same screen again. What I'm interested in is that test statistic and the p-value. Now this, again, is just a copy over of my 2 hypotheses for this particular test. I'm starting off by saying my null is that they're independent, and then the alternate is that they're dependent. So now, the critical value never comes from doing a test. Critical values always come from an inverse. So we're going to have to do the chi-square distribution table to find the critical value. And I'm going to go ahead and go to the next slide. We're going to come back to this one in just a minute. Okay? So here's the thing. The chi-square distribution, you don't have an inverse chi-squared. So you're going to have to use a table, kind of like we used a table on our previous section for some things. But what we do know is that my calculator told me that my degrees of freedom was 3. And I know from my earlier problem, let's just go back and look at this, it said use a 5% significance level. Chi-square are always right-tailed test. And notice it says the area to the right. So my 5% is in the right. And I know that this can throw you off because your calculators want to do a lot of things from the left, but this one's coming from the table, and this area is always to the right. So we're going to have 5% in the right-hand section. And then my degrees of freedom was 3. So if you go across there, I have then a critical value at 7.815. Then I can use my 2 methods. I have 2 different methods to look at it. Okay? Now, first of all, if the p-value is less than alpha, we're going to reject it. Now, this p-value, and we've talked about this before, has this e to the -12, so that decimal's got to move 12 places to the left. So this is essentially 0. And that is definitely less than alpha. So we would conclude that we should reject. Now, the critical value method should give us the same answer. But the way we do the critical value method is chi-squared actually doesn't look quite like that. A chi-squared distribution, this isn't critical to you, but instead of having that big hill in the center, it's a little bit more skewed to the right. So we kind of end up with this big hill and then this longer tail over here. So at any rate, though, our critical method, what happens is our critical value, which we found to be 7.815, is cutting off this tail. However, our test statistic is to the right of that 7.815. 58.393 is actually way over here to the right, you know, but it is in the critical region. So since it's in the critical region, then we should reject. So again, we got the same conclusion. So this is easier than many of the things you've done because we just had to type in the numbers they gave us. We have a chart that you're going to use the critical value from. Now, there is a critical value chi-square distribution table that's in the back of your textbook, or there's a page number for it. But generally, it's going to be a pop-up. You're going to have something on your homework that says you can click here to see the chi-square distribution table. Here it is, a larger version, one that has a lot more rows, is on page 703 in the online textbook. It's labeled Table A4. You can also just do a chi-square distribution table search in Google and find it. But most of the time, I believe maybe on every single homework problem, you're just going to have to click it, and it's going to open up the section of the table you need to see, just kind of like this. So they're always right-tailed, and you'll find your critical value from the table. So we're just had to type in a few numbers and then click on that to get that test. It is quite a few clicks, I get that. But then expected value is the other thing they can ask you about. Now, if you need an expected value for a particular cell, every single cell, you can do the row total times the column total divided by the grand total. So if you needed to know the expected value for the first thing, you would take the first row total times the first column total divided by the grand. If you needed to calculate this value of 18.52, it would be the first row times the second column divided by the grand total. So you could do that. However, you don't really have to, because again, when we did our test, we told it to put the outcomes in matrix B. So now I just need to look at what matrix B says. So to do that, we go back into our matrix menu and hit B. It's just that simple. So here I'm going to quit this. I'm going to go second x to the negative 1, which is the matrix. I know that the expected values got put in matrix B, so I hit enter. And then that's not showing it to me yet. So to get it to show it to you, you hit enter again. And here are all of those expected values. And again, it may ask you, does it meet the requirement of expected values before it asks you to run the test? But the easiest thing for you to do is run the test first, then look at your matrix B. This is where I can verify that every expected value was greater than 5, including this one. This is the smallest expected value I have. So you do need to verify that all the expected values are greater than 5. Just go ahead and run the test and then look at your matrix B. In doing this then, if you would prefer, I use the calculator on these. I find that very easy, and there's not a lot of numbers to enter. If you want to take a screenshot of that or snap a picture of it, this is the key to how to do. You've got to enter your stuff in matrix A, then do your chi-square test. Your observed is A, unless you entered it somewhere else. Your expected is B, and it's going to create those expected values for you. You get out a test statistic and a p-value. And then additionally, you can go back and look at what your expected values are. So if your expected values here are less than 5, then the test results might not be valid. But rather than have you have to calculate them for each one of those numbers yourself, this is the easiest way. If you prefer StatCrunch, because a lot of times you can open it in StatCrunch, I find that this one is not easier in StatCrunch, but there are a lot of videos online about how to do this in StatCrunch. Down here, that looks like a typo, but I swear to you, I copied and pasted it. But you can just do a chi-square test of independence and then put StatCrunch behind it. And it's just going to give you, as you can see, tons of videos or tons of listings. And then you can click videos about using that in StatCrunch if you want to. Again, I just use the calculator. It's not a lot of numbers to enter. And that, guys, actually finishes up our very last lesson. All right, guys, that's it. Thanks.